Hi, myself Dr. S.K. Boishya, former HOD, Department of Physics, Cotton University. This is a video lecture in physics for class 12 students, and the topic is electrostatics. Lesson 5 of Chapter 2 on Capacitors and Capacitance, Part 2. In this lesson, we'll consider series and parallel combinations of capacitors and a few numerical problems. Let's begin. Combination of capacitors. A number of capacitors may be connected in a circuit as a combination. In the adjoining figure, a group of 3 capacitors has been connected across A and B in a circuit. We are interested in finding a single capacitor equivalent to the given combination. Suppose the combination in the figure and a single capacitor C are equivalent. Then, if the combination and the single capacitor were put in a box with just the terminals A and B protruding out, it would be impossible to identify the two by electrical measurements external to the box. There are two basic combinations of capacitors: series combination and then parallel combination. Any combinations of capacitors, however complex it may be, could ultimately be broken down into a number of simple series and parallel combinations. Series combination of capacitors. The figure shows 3 capacitors C1, C2, and C3 connected in series. The magnitude of charge Q on each plate will be identical. The battery, which is connected across A and B, will only produce charge separation, and hence the net charge on the plates, for example, on those within the dashed region, must remain zero before and after the connection. It is impossible for charge to enter or leave the region enclosed by the dashed lines. In series, the total potential drop V across the capacitors is the sum of potential drops V1, V2, and V3 across the individual capacitors. That is V equal to V1 plus V2 plus V3, that is equation 1. Applying the relation Q equal to CV to each capacitor, we get V1 equal to Q by C1, V2 equal to Q by C2, and V3 equal to Q by C3. Combining equations 1 and 2, we arrive at the equation 3. Using equation 3, the equivalent capacitance C is obtained as in the equation. And finally, we get 1 by C equal to 1 by C1 plus 1 by C2 plus 1 by C3. We call it equation 4. This is the final result and is true for n number of capacitors connected in series. Now, parallel combination of capacitors. The figure shows 3 capacitors C1, C2, and C3 connected in parallel. The potential difference across each capacitor will be identical as all of the leg plates are connected together and to the terminal A, whereas all of the right plates are connected together and to the terminal B. The charges on the capacitors are respectively Q1, Q2, and Q3. Applying the relation Q equal to CV to each capacitor, we get Q1 equal to C1V, Q2 equal to C2V, and Q3 equal to C3V. We call it equation 1. The total charge Q on the combination is distributed on the capacitors as Q equal to Q1 plus Q2 plus Q3. Then using equation 1, Q equal to C1V plus C2V plus C3V equal to bracket start C1 plus C2 plus C3 bracket close into V. This is equation 2. The equivalent capacitance C is obtained as C equal to Q by V. Therefore, C equal to C1 plus C2 plus C3. We have used equation 2 to arrive at this result. This is the final result and is true for n number of capacitors connected in series. Problems. Number 1. Establish a relationship between charge density, we call it sigma, and the curvature of the surface of a conductor. Let us consider two spheres of different radii connected by a very long thin wire. The entire assembly has been maintained at a common potential V. Let us say that. This is the diagram. Exploiting the identical potential of the spheres, we may write V equal to 1 by 4 pi epsilon naught Q1 by R1 also equal to 1 by 4 pi epsilon naught Q2 by R2, or Q1 by Q2 equal to R1 by R2. This is equation 1. Here Q1 and Q2 are the charges on the spheres of radii R1 and R2 respectively. Equation 1 tells us that the bigger sphere contains greater amount of charge. The surface charge density on the spheres are respectively sigma 1 equal to Q1 divided by 4 pi R1 square and sigma 2 equal to Q2 divided by 4 pi R2 square. Or sigma 1 by sigma 2 is equal to Q1 by Q2 multiplied by R2 square divided by R1 square. We call it equation 2. Substituting Q1 by Q2 from equation 1 in equation 2, we get sigma 1 by sigma 2 equal to R2 by R1. This is equation 3. Thus, sigma proportional to 1 by R. This is equation 3. That is, the charge density sigma is inversely proportional to the radius, that is proportional to the curvature of the sphere. Equation 3 tells us that the bigger sphere holds lesser surface charge density compared to the smaller one. Number 2, a small sphere of radius smaller is placed concentrically inside a large spherical shell of radius capital R. The charges on the spheres are small q and capital Q respectively. Find the potential difference between the spheres. This is the situation in diagram. The potential of the larger shell is contributed by its own charge and also by those on the smaller sphere. Potential V of the larger sphere is equal to 1 by 4 pi epsilon naught capital Q by capital R plus 1 by 4 pi epsilon naught small q by capital R. This is equation 1. The first term is its own contribution, while the second term is that of the inner sphere. Similarly, the potential of the smaller sphere is contributed by its own charge and also by those on the bigger shell. So potential of the smaller sphere is equal to 1 by 4 pi epsilon naught small q by smaller plus 1 by 4 pi epsilon naught capital Q by capital R. This is equation 2. As before, the first term is its own contribution, while the second term is that of the outer cell. Now, the potential difference between the conductors is delta V, we call it delta V, equal to potential of the smaller sphere minus potential of the bigger sphere. We put the values and we get this expression. The final result is Q by 4 pi epsilon naught, bracket start, 1 by smaller minus 1 by capital R, bracket close. This is equation 3. Now, the quantity inside the bracket, that is 1 by smaller minus 1 by capital R, is always greater than 0. Therefore, if Q is positive, the inner sphere will always be at a higher potential than the enclosing cell. Number 3, a parallel plate capacitor is filled with two dielectrics of identical dimensions as shown in the figure. Find the modified capacitance. The arrangement is equivalent to two capacitors in series, each of area A and separation d by 2. Therefore, the capacitance of the system is 1 by C equal to 1 by C1 plus 1 by C2, where C is the capacitance of the system. Substituting the values for C1 and C2, we get this equation. Therefore, C is equal to, as seen in the equation, and final expression is C equal to C naught within bracket 2K1 K2 divided by K1 plus K2, where C naught equal to epsilon naught A by D is the capacitance of the parallel plate capacitor without the dielectric. Number 4, a parallel plate capacitor is filled with two dielectrics of identical dimensions as shown in the figure. Find a modified capacitance. The arrangement is equivalent to two capacitors in parallel, each of area A by 2 and separation D. Therefore, the capacitance of the system is C equal to C dash plus C double dash. Substituting for C dash and C double dash, we get C equal to this. And finally, C equal to C naught within bracket K1 plus K2 divided by 2, where C naught equal to epsilon naught A by D is the capacitance of the parallel plate capacitor without the dielectric. Number 5, the separation between the plates of a parallel plate capacitor is D and the area of its plate is A. A dielectric slab of thickness T, which is less than D and of the same area, is inserted completely between the plates. Find a modified capacitance. Let Y be the separation between the dielectric slab and one of the plates. If V is the potential drop across the capacitor, then V is equal to V1 plus V2 plus V3, equation 1. We'll be defining V1, V2 and V3 in the next slide. Here, V1, V2 and V3 are respectively the potential drops across the regions 1, 2 and 3 inside the capacitor. Now, since the potential drop V is equal to electric field E multiplied by distance, we can express V as E1 into Y plus E2 into T plus E3 into, within bracket, D minus Y minus T. This is equation 2. Here E1, E2 and E3 are the electric fields in the regions 1, 2 and 3 inside the capacitor. As electric field E is equal to sigma by epsilon, that is sigma by epsilon naught K, where epsilon naught is the permittivity of free space and K is the dielectric constant of the slab, we have V as given by equation 3. Further simplification leads us to equation 4. As charge density sigma is equal to Q by A, we get V equal to, as given by equation 5. Now, capacitance C is equal to Q by V. Substituting Q by V, we get this expression for C, epsilon naught A divided by Y plus T by capital K plus, within bracket, D minus Y minus T, which further simplifies to, as given by equation 6. That is epsilon naught A divided by, within bracket, D minus T, bracket close, plus T by K. Remarks. The modified capacitance is independent of Y, that is independent of the position of the dielectric slab within the capacitor as long as it is wholly inside the plates. If the entire space between the plates is filled up with the dielectric, then C is finally equal to K into C naught, where C naught is equal to epsilon naught A by D is the capacitance without the dielectric. Number 6. The separation between the plates of a parallel plate capacitor is D and the area of each plate is A. A metal slab of thickness B, which is less than D and of same area, is inserted completely between the plates. Find the modified capacitance. With the insertion of the metal slab, the original capacitor becomes a system of two capacitors in series as shown in the figures in the next slide. The first figure simply shows the metal slab inside the capacitor. The second figure illustrates the effective situation. The metal slab is, in fact, the sum of two metal plates connected by a metal wire. This is the effective situation, and we have this condition as the metal slab is an equipotential. Now, if C is the modified capacitance, then 1 by C is obviously equal to 1 by C1 plus 1 by C2. We substitute the values for C1 and C2, get this. A further simplification will lead us to the result 1 by C equal to D minus B divided by epsilon naught A. Therefore, C is equal to epsilon naught A divided by D minus B. Remarks. The modified capacitance is independent of Y, that is independent of the position of the metal slab within the capacitor as long as it is wholly inside the plates. The capacitance of the system increases with the insertion of the metal slab. Number 7. Both the capacitors in the figures contain equal amount of charge. What happens to the voltmeter reading when a dielectric slab is inserted between the plates of the right-hand side capacitor? As discussed earlier, the appearance of bound charges in a dielectric reduces the electric field and hence the potential difference across the capacitor also decreases. Number 8. The battery B supplies the same potential difference to each capacitor. What happens to the right-hand side capacitor when a dielectric slab is inserted between its plates? As the potential difference across the plates has been pegged at a given value, the enhanced capacitance in presence of the dielectric leads to higher charge in the capacitor. Number 9. Is it possible to charge a metal sphere of radius 1 meter with 1 coulomb of charge? Let us assume that it is possible. Then the field near the sphere would be E equal to 1 by 4 pi epsilon naught Q by R square equal to 9 into 10 to the power 9 into 1 by 1 square equal to 9 into 10 to the power 9 volt per meter. But the dielectric strength of air is 3 into 10 to the power 6 volt per meter. Therefore, the charges from the sphere will start leaking much before it attains 1 coulomb of charge. So the answer is no. Regarding the asterisks, beyond this limit, that is the limit of dielectric strength, air becomes conducting. Number 10, find the capacitance of the earth considered as a perfect sphere of radius 6400 km. The capacitance of a sphere is C equal to 4 pi epsilon naught into R. Substituting the values, C equal to 1 divided by 9 into 10 to the power 9, then multiplied by 6400, then multiplied by 10 to the power 3, equal to 7.1 into 10 to the power minus 4 Farad. This brings us to the end of lesson 5 of chapter 2. We'll pick up a few problems involving groupings of capacitors in the next lesson. Till then, goodbye and thank you.